You hear 68 kilometers per second and think you understand speed. You don't. That's 151,000 miles per hour. That's the velocity 3I Atlas will hit when it reaches perihelion on October 29th, 2025, screaming past the sun at 1.36 astronomical units. Inside the orbit of Mars, close enough to cook, fast enough to escape. This isn't some neighborhood rock on a lazy ellipse. This is an interloper from deep space, the third confirmed visitor from beyond our solar system. And it's moving like nothing we've ever tracked before. Discovery happened July 1st, 2025, when the Atlas telescope in Rio Hurtado, Chile, caught a faint smudge against the star field, 420 million miles out. The automated system flagged it immediately. Not the brightness, the trajectory. Engineers ran the numbers 3 times. Hyperbolic orbit, excess velocity 58 kilometers per second relative to the sun. That's escape velocity with room to spare. By July 5th, confirmation came from observatories worldwide. Pre-discovery images surfaced from Zwicky Transient Facility dating back to June 14th. Even TESS caught it in May, 6.4 astronomical units from the sun, already active, already outgassing. This thing had been cooking for months before anyone noticed. Why? It was passing through Sagittarius, right in front of the galactic center's dense star fields. Thousands of stars per square degree. Finding one moving dot in that mess is like spotting a single firefly in a forest fire. If you value documented interstellar astronomy and deep space chemistry like this, subscribe, as it's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual. Using sources from NASA's official 3I Atlas mission page published July 3rd, 2025, the peer-reviewed archive paper 2508.18209 by Martin Cordner and team published August 25th Farce. 2025 on James Webb Space Telescope Spectroscopy, and the Very Large Telescope Nickel Emission Study published August 25th, 2025 by Rahat Gaonkar and collaborators. Now back to the information. Hubble caught it first in detail. On July 21st, 2025, 277 million miles from Earth, the image shows a teardrop-shaped cocoon of dust, a coma roughly 18,800 kilometers wide, and a faint tail pointing away from the sun. Not spectacular, not bright, but unmistakably active. The nucleus sits somewhere inside that glow. Hubble's measurements, refined through August 20th, put the diameter between 440 meters and 5.6 kilometers. Most likely less than 1 kilometer, small, dense, ancient. David Jewett at UCLA led the observations. He said you can't trace this thing back with any accuracy. It's like glimpsing a rifle bullet for 1,000th of a second. You see the trajectory, but not the gun. The comet has been traveling through interstellar space for billions of years. Gravitational interactions with stars and nebulae have scrambled its path. No way to pinpoint the parent system. But we know the direction. It arrived from Sagittarius, from the thick disk of the Milky Way. Matthew Hopkins at Oxford ran the numbers in July 2025 using the Otauta High Oxford Interstellar Object Population Model. The vertical velocity component is high, 18.5 kilometers per second upward through the galactic plane. That's not thin disk behavior. Thin disk objects orbit close to the galactic plane. Velocities under 10 kilometers per second vertical. Thick disk objects have tilted orbits, higher vertical speeds, older ages. Hopkins estimates 3I Atlas formed between 7.6 and 14 billion years old with 68% confidence. Independent analysis by Astor Taylor and Daryl Seligman in July 2025 agrees 3 to 11 billion years. Older than the solar system by at least 3 billion years, possibly by 9 billion years. This comet formed when the universe was less than half its current age. It orbited a star that may have died billions of years before Earth existed. It's been drifting through the void ever since. A relic from cosmic noon, August 6th, 2025. James Webb Space Telescope turned its near-infrared spectrograph on 3I Atlas, distance 3.32 astronomical units from the Sun. The spectrum spans at 0.6 to 5.3 micrometers. The results shattered expectations. Carbon dioxide dominates the coma. CO2 to H2O mixing ratio 7.6 plus or minus 0.3, 8 to 1. Carbon dioxide to water. That's the highest ratio ever observed in a comet at that distance from the Sun. The published archive paper 250.8.1.8209 by Cordner and team calls it 4.5 sigma, above the trend for long period and Jupiter family comets. Statistical outlier, chemical rebel. The spectrum also shows water ice, water vapor, carbon monoxide, carbonyl sulfide, and dust. But carbon dioxide is king. 87% of the gas by mass. Water makes up 4%, carbon monoxide 9%. This isn't how comets work in our neighborhood. Solar system comets supplement water as their primary volatile. Water drives the activity, creates the pressure, lifts the dust, but 3, I-Atlas, runs on dry ice. The carbon dioxide sublimation rate at 3.32 astronomical units suggests an intrinsically CO2-rich nucleus. Either it formed far from its parent star, beyond the carbon dioxide frost line where temperatures allow CO2 to freeze, or it was exposed to extreme radiation that processed the ices over billions of years. Cosmic rays can break molecular bonds, alter ratios, create chemical signatures we don't see in young objects. SphereX Space Observatory confirmed the finding in mid-August 2025. Detection of bright carbon dioxide emission and water ice in near-infrared bands. The 1 micrometer flux suggests a large reflecting surface. Avi Loeb at Harvard calculated a diameter of 46 kilometers based on that data, though he notes the mass discrepancy. If true I-Atlas is 46 kilometers wide, its mass would exceed the previous interstellar comet 2I, Borisov, by a factor of 1 million. We should have discovered 1 million Borisov-sized objects before finding one giant. The interstellar density of rocky material is too low by a factor of 10,000 to deliver a 46-kilometer object into the inner solar system over Atlas's decade-long survey. Either the nucleus is much smaller and surrounded by a dense dust coma reflecting most of the sunlight, or something else is going on. Loeb suggests checking with radio telescopes for technological transmissions. He's half joking. Mostly. July 20th, 2025. Very large telescope in Chile detected nickel vapor in the coma. Atomic nickel, 1 emission lines in the ultraviolet spectrum. Not unusual. 2I Borisov showed nickel. Solar system comets show nickel. Nickel and iron come together from supernova ejecta, locked in refractory minerals. Heat the surface, sublime the volatiles. The dust carries metal atoms. Except 3, I-Atlas shows nickel without iron. August 21st, 2025, VLT spectroscopy confirmed. Nickel emission rate 4.6, plus or minus 0.7 grams per second. Iron? Barely detectable. The nickel to iron ratio is orders of magnitude higher than any known comet. Natural objects show nickel and iron together, always. The ratio varies, but both metals appear. Decoupling them requires chemistry we don't see in nature, industrial refining, carbonyl processes, nickel-titanium alloys used in shape memory applications. On Earth, separating nickel from iron is a metallurgical process. In space, unknown. Rahat Gankar and team's August 25th paper on Archive shows the production rates increasing steeply. The nickel emission follows a power law with heliocentric distance to the minus 8.43 plus or minus 0.79. Get closer to the sun, nickel production explodes. By August 21st, at 2.85 astronomical units, the rate had climbed from under 1 gram per second at 4.4 astronomical units to nearly 5 grams per second. Projection to perihelion, tens of grams per second, maybe more. Cyanide appeared next, August 14th, 2025. VLT detected CN emission lines. Mass loss rate 17.6, plus or minus 2 grams per second at 2.85 astronomical units. Power law dependence minus 9.38, plus or minus 1.2. Even steeper than nickel. By September 7th, 2025, the comet turned green. Michael Jaeger and Gerald Riemann's imaging showed the color shift from red to green-blue. Cyanide does that. CN emission peaks in the green part of the spectrum. The James Clerk Maxwell Telescope measured hydrogen cyanide on September 7th at 2.33 astronomical units. Production rate 1.5 plus or minus 0.5 times 10 to the 25th molecules per second. 1 week later, September 14th, the rate tripled, 4.5 plus or minus 1.9 times 10 to the 25th molecules per second. 2 kilograms per second of hydrogen cyanide. The coma on September 15th measured 180,000 kilometers across, asymmetric, seeing elongated in the anti-solar direction. Dust tail visible, 50 arc seconds wide, about 100,000 kilometers long. Apparent magnitude, 14.2. Faint, too dim for amateur scopes under 8 inches, but growing, brightening, accelerating toward peak activity. Gemini South caught the tail on August 27th, 2025. Deep imaging with the Gemini multi-object spectrograph in 4 bands. UGEREI, centered on wavelengths 0.365, 0.467, 0.616, and 0.747 micrometers. The images show a teardrop-shaped anti-solar tail about 30 arc-seconds long, 56,400 kilometers, pointing southeast. The coma spread to 10 arc-seconds, 18,800 kilometers, much larger than the compact appearance in early July. Dust particles blown by solar radiation pressure. Small grains ejected at high speeds. The broadness suggests rapid sublimation, violent outgassing, material streaming off the surface faster than normal. Carbon dioxide does that. Dry ice sublimates at lower temperatures than water ice. At 3 astronomical units, water barely moves. Carbon dioxide boils. The sun heats the nucleus. Subsurface CO, 2 pockets warm, expand, fracture overlying layers, burst through. Each jet adds velocity to the dust. Each vent creates asymmetry. The sunward side glows brighter. Enhanced outgassing toward the sun, visible in James Webb's spectral images. The comet is cooking unevenly. Mars approach. October 3rd, 2025 to 0400 UTC. Closest distance 29 million kilometers, 18 million miles. Mars orbiters ready. ESA's Mars Express and ExoMars Trace Gas Orbiter locked on between October 1st and 7th. Instruments include high-resolution stereo camera and color and stereo surface imaging system. Cameras designed to photograph Martian surface from orbit. Not ideal for a 30 million kilometer target, but they'll try. Spectrometers too. Omega, SpyCam, Nomad. Measuring light composition if the comet's bright enough. NASA's Mars. Reconnaissance orbiter joins the watch. High-rise camera capable of 30 kilometer per pixel resolution at Mars distance. 20 times better spatial resolution than Hubble's July image. The brightest pixel will gauge surface area, constrained diameter. Perseverance and Curiosity rovers might catch a glimpse. Limited instruments, but unique vantage point. From Mars, 3. I-Atlas reaches apparent magnitude 11. Barely visible, but observable. The fleet watches Europe and America together. First time multiple spacecraft coordinate observations of an interstellar object from another planet. Historic. Unprecedented. The data won't arrive for weeks. Transmission delays, data processing, analysis, but the observations happen now. October 2025. While 3, I-Atlas races toward perihelion and Earth can't see it because the sun is in the way. Perihelion October 29, 2025, 11:44 UTC plus or minus 1 minute, distance 1.36 astronomical units, 203 million kilometers, 126 million miles, just inside Mars orbit. The comet will be moving 68 kilometers per second, 151,000 miles per hour. Escape velocity from the solar system at Mercury's orbit is 68 kilometers per second. 3. Play. I-Atlas at Mars distance matches that. It's moving fast enough to escape from closer to the sun than it actually is. Hyperbolic excess velocity, 58 kilometers per second. That's the speed it had when it entered the solar system. The sun added 10 kilometers per second as the comet fell inward. At perihelion, total velocity peaks. After perihelion, the sun's gravity slows it again. By the time 3, I-Atlas, crosses Jupiter's orbit outbound in March 2026, it will be back to 58 kilometers per second relative to the sun forever. The comet will never stop, never return. It came from the thick disk, passing through the thin disk where we live, slingshotting around the sun and heading back out. Trajectory tilted 5 degrees to the ecliptic. Retrograde motion, moving backward relative to planetary orbits. The alignment is suspicious. 1 in 500 chance for a random interstellar object to match the ecliptic so closely. Avi Loeb notes this. He notes everything. The alignment, the mass, the nickel without iron, the carbon dioxide dominance, the trajectory toward Mars and Jupiter. He suggests checking for radio signals. Most scientists roll their eyes. Loeb doesn't care. He's been here before with Oumuamua. He'll follow the data wherever it leads, even if it leads somewhere uncomfortable. November 2025. ESA's Jupiter Icy Moons Explorer will observe 3 I-Atlas for 3 weeks. November 2nd through 25th, multiple instruments, cameras, spectrometers, particle sensors, coordination with NASA's Europa Clipper considered, twin ultraviolet spectrographs, 1 on each spacecraft. Compare notes, cross-check measurements. JUICE sits on the far side of the sun from Earth. Data transmission slow, using medium gain antenna because high gain antenna acts as heat shield this close to the sun. Results won't arrive until February 2026, but JUICE will see the comet in its most active state. fresh from perihelion. Heated, outgassing, tail fully extended, coma, bright and broad, peak carbon dioxide sublimation, peak nickel emission, peak cyanide production. The chemistry will be on full display. Whatever 3. I-Atlas is made of. Whatever processes created its bizarre composition, JUICE will see it unleashed. December 2025, James Webb observes again. Hubble continues ultraviolet spectroscopy, monitoring composition as the comet retreats. Sulfur to oxygen ratio measurements, gas emission tracking. The telescopes will follow. 3 I-Atlas until it fades below detection limits. Months, maybe a year. Depends on activity levels, depends on dust production, depends on whether the nucleus stays intact or fragments under thermal stress. Comets do that. 2 I-Borisov fragmented, broke apart near perihelion, thermal shock, structural failure. But 3 I-Atlas seems stable so far. No outburst detected as of September 2025. Brightness steady. Activity predictable. The nucleus might be tougher than expected. Billions of years drifting through space. Cosmic ray bombardment. Micrometeorite impacts. The surface could be armored. Sintered. Heat treated by interstellar radiation into something harder than fresh cometary ice. The composition tells a story. Carbon dioxide richness suggests formation beyond the CO2 frost line. In our solar system, that's around 5 astronomical units, Saturn's distance. In another system, depends on the star's luminosity. A dim red dwarf pushes frost lines inward. A bright young star pushes them outward, but CO2 forms farther out than water in any system. The ratio indicates a cold birth. Outer disk, where temperatures allow carbon dioxide to condense but water remains scarce. Or radiation processing. Billions of years exposed to galactic cosmic rays, energetic particles slamming into surface ices. Breaking bonds, preferentially removing hydrogen. Water loses hydrogen easily. H2O becomes OH becomes O. Carbon dioxide is more stable. C equals O, double bonds harder to break. Over time, a water-rich comet irradiated in interstellar space could become carbon dioxide rich through differential destruction. The surface ices we see might not match the interior. The coma might reflect processed surface material while the nucleus holds pristine water ice underneath. That would explain the low water detection. A crust, a carbon dioxide-rich crust insulating a water-rich core. The heat from perihelion could break through, could crack the crust, could release the water. We'll know in late October when 3 I-Atlas passes the Sun and the Mars fleet watches from 30 million kilometers away. The thick disk origin matters. Matthew Hopkins's Otautahai Oxford model uses Gaia data, Milky Way chemistry models, and stellar kinematics. The vertical velocity component places 3 I-Atlas in the thick disk population. Stars, there are older, metal poor, formed when the galaxy was young, heavy element abundance at least 40% of solar. Lower metallicity means different planet formation, different disk chemistry. Less dust, less rocky material, more ices. Giant planets form faster in metal-poor disks, if they form at all. Comet populations differ. Composition shifts toward volatiles. Carbon and oxygen compounds dominate over silicates. 3 I-Atlas might represent typical thick disk comet composition, or it might be an outlier even there. We can't know until we find more. The Vera Rubin Observatory will help. Legacy survey of space and time starts soon. 10-year survey. Expected to find 5 to 50 interstellar objects per year, maybe more. Depends on size distribution, depends on number density in the local interstellar medium, depends on our detection limits and survey cadence, but the sample will grow. We'll stop treating each interstellar visitor as unique. We'll start seeing patterns, families, chemical signatures, dynamical groups. We'll build a taxonomy of extrasolar objects the way we have for asteroids and comets. 3. I-Atlas is just the beginning. The age estimate changes everything. 7.6 to 14 billion years. The Sun formed 4.6 billion years ago. Earth 4.5 billion. Life on Earth 3.8 billion years at least. 3. I-Atlas predates all of it, by billions of years. It formed when the universe was 2 to 6 billion years old, when the Milky Way's thick disk was assembling, when star formation rates peaked during cosmic noon. The parent star could be dead, could have gone supernova billions of years ago. The planetary system could be gone, destroyed, scattered, consumed. Only the comets remain, ejected during formation, kicked out by giant planets, sent into interstellar space. Wandering, 3 I-Atlas wandered for 10 billion years, give or take, circling the galactic center, drifting through spiral arms, passing thousands of stars, Never captured, never destroyed, until July 2025, when it happened to pass through a tiny patch of space we're monitoring, 420 million miles from a yellow dwarf star in the Orion Arm, a star with planets. One planet with telescopes. We saw it. We're tracking it. We're measuring it. And in a few months it will be gone, never to return. Back into the dark, back into the deep, back to wandering the thick disk for another 10 billion years, unless it hits something. Unless another system captures it, unless it fragments, unless something we can't predict happens, but most likely it just keeps going. Silent, ancient, alone, the speed proves it. 68 kilometers per second at perihelion. That velocity doesn't happen by accident. That's not a gravitational slingshot from Jupiter. That's not orbital velocity. That's hyperbolic departure. The comet entered the solar system already moving 58 kilometers per second. The sun added 10, it will leave moving 58. The kinetic energy is immense. Mass times velocity squared over 2. Even a small nucleus carries gigajoules. If 3 I Atlas is 1 kilometer across and density is 500 kilograms per cubic meter, typical for comets, mass is roughly 2.6 times 10 to the 11th kilograms. Velocity, 58,000 meters per second. Kinetic energy, 4.4 times 10 to the 20 joules. That's 105 megatons TNT equivalent. Tsar Bomba was 50 megatons, the biggest nuclear weapon ever detonated. 3. I Atlas carries twice that energy just from speed. Impact with Earth would be extinction level, won't happen. Closest approach, 1.8 astronomical units, 270 million kilometers, 167 million miles, December 19th, 2025. Safe, totally safe, but the energy is there. Stored in velocity, ancient kinetic energy from a birth system we'll never see. The silence from Mars was deafening, not literal silence, but the radio silence of data transmission. For 2 weeks after the October 3rd flyby, the scientific community held its collective breath. The European Space Agency and NASA confirmed their Martian flotilla had performed flawlessly. Mars Express, the Trace Gas Orbiter, and the Mars Reconnaissance Orbiter had all slewed their instruments to track the fleeting visitor. On the surface, Perseverance and Curiosity had pointed their cameras skyward, but the data was a slow trickle, traveling across tens of millions of kilometers of interplanetary space, queued in buffers, downlinked through the Deep Space Network, and routed to processing centers in Darmstadt and Pasadena. The world waited. And while it waited, 3 I Atlas continued its inexorable plunge toward the sun. By October 15th, 2025, the comet had brightened to magnitude 13, still a challenge for amateurs, but a beacon for professional observatories. The green coma, fueled by diatomic carbon and cyanide, had swelled to over 200,000 kilometers in diameter. The dust tail, once a faint smear, now stretched over 1 million kilometers, a pale yellow ribbon against the black. The rate of change was astonishing. Ground-based telescopes reported the nickel emission had doubled again, now approaching 10 grams per second. Hydrogen cyanide production was a torrent, nearing 5 kilograms per second. The comet was shedding mass at a furious pace, a celestial iceberg melting not in water, but in a fire of its own volatile chemistry. The question on everyone's mind was simple. What did Mars see? The first high-rise image from the Mars Reconnaissance Orbiter was released to the public on October 18th, 2025. It was, at first glance, a disappointment. A single, overexposed pixel. The core of the coma was so bright, so dense with dust, that the super high-resolution camera was saturated. The team at the University of Arizona had expected this. They released a second image, processed with extreme prejudice, filtering out 99.9% of the light. What remained was ghostly, not a single nucleus, but a tight cluster of at least 3, perhaps 4 distinct points of light, embedded in a shared teardrop-shaped haze. The primary object was estimated to be no more than 800 meters across. The companions were smaller, perhaps 100 to 200 meters each. They were tumbling, separated by only a few kilometers. 3CO, I Atlas, was not a solid body. It was a rubble pile. Or it was in the process of becoming one. This changed the interpretation of the Hubble data. The earlier size estimate, between 440 meters and 5.6 kilometers, now made sense. They weren't seeing a single object. They were seeing a gravitationally bound swarm. This also began to explain the violent, asymmetric outgassing. The sun wasn't heating a single, rotating body. It was cooking a collection of fragments, with sunlight penetrating the gaps between them, heating surfaces that would normally be in shadow. It was a cascade failure in slow motion. Billions of years of interstellar travel had ended in a chaotic breakup just as it reached the inner solar system. Then came the spectrometer data from the Trace Gas Orbiter's NOMAD instrument. The data confirmed the carbon dioxide dominance in spectacular fashion. The CO2 signature was so strong it drowned out almost everything else, but deep in the noise, after weeks of analysis, the team found something new, a faint but unmistakable absorption line for methane. And not just any methane. The isotopic signature was heavy. It was rich in deuterium, the heavy isotope of hydrogen. The deuterium to hydrogen ratio in the methane was staggeringly high, 5 times higher than any comet in our own solar system. This pointed to an origin in an extremely cold, dense molecular cloud, far colder than the nebula that formed our own sun. A place where deuterium could more easily bond with carbon, preserved in frozen methane for eons. The comet wasn't just old, it was born in a fundamentally different, colder environment than anything we knew. As perihelion approached, the tension was palpable. October 29th, 2025, and the day the comet would feel the sun's maximum fury. All eyes were on the Solar and Heliospheric Observatory, SOHO, and the twin stereo spacecraft. They were the only probes positioned to watch the close pass, as from Earth's perspective, the comet was lost in the sun's glare. Amateur astronomers were out of luck, but the world's solar telescopes were locked on. At 1144 Coordinated Universal Time, 3. Atlas reached its closest point to the sun, 126 million miles, screaming past at 151,000 miles per hour. For 3 days, the data from SOHO's coronagraphs was a tantalizing mystery. The instrument, designed to block the sun's direct light to see the faint corona, showed a massive plume erupting from the comet's position. It wasn't a normal tail, it was a vast, expanding cloud, a coronal mass ejection, but in miniature, originating not from the sun, but from the tiny interstellar visitor. On November 1st, when the analysis was complete, the announcement came. At perihelion, the primary 800-meter fragment had disintegrated. The thermal stress was too much. The rapid heating caused subsurface pockets of frozen carbon dioxide and now, presumably methane, to flash vaporize. The pressure built until it exceeded the structural integrity of the ancient, irradiated ice. The nucleus blew apart. The SOHO data showed the cloud of debris expanding at over 500 meters per second. The once coherent cluster of fragments was now a rapidly dispersing shotgun blast of ice and rock. 3I Atlas, the billion-year-old wanderer, had died in a blaze of glory. This event, however tragic for the object itself, was a scientific goldmine. The explosion had excavated the comet's interior, exposing material that had been shielded from interstellar radiation for billions of years. This was the moment the Jupiter Icy Moons explorer, JUICE, had been waiting for, positioned perfectly for the aftermath. JUICE began its 3-week observation campaign on November 2nd. Its particle detectors and ultraviolet spectrograph were aimed at the expanding cloud of debris. The first results from JUICE, received on Earth in slow, painstaking packets through its medium-gain antenna, began arriving in late November and were nothing short of revolutionary. The ultraviolet spectrum of the fresh material was completely different from the pre-perihelion coma. The carbon dioxide signature was still there, but it was no longer dominant. Suddenly, water was everywhere. The H2O signal surged, becoming the most abundant volatile by a factor of 3. The theory of a processed CO2-rich crust insulating a water-rich interior was confirmed in the most dramatic way possible. The comet had worn a disguise, a thin layer of dry ice created by eons of cosmic ray bombardment. Its true heart was water, just like the comets of our own solar system, but the other mysteries only deepened. As JUICE's Janus camera attempted to resolve the largest remaining fragments, its particle detector, the particle environment package, began registering impacts, not just dust grains, but something bigger, microscopic, metallic particles. The composition sensor analyzed them. They were almost pure nickel. The nickel without iron problem was not just a gas phase anomaly in the coma, it was a solid-state reality in the dust. The comet was shedding tiny flecks of refined nickel. Avi Loeb's office at Harvard became the center of a firestorm of speculation. His earlier half-joking suggestions about technological signals were now being discussed with a nervous sobriety. Natural processes that could create pure nickel grains in a comet were unknown. Could extreme radiation differentiate the elements? Could some bizarre chemical process in a protoplanetary disk create nickel-rich sulfides that release their metal content without iron? The theories grew more exotic by the day. One paper proposed that the parent star had been a rare type of supernova, an iron-poor core collapse event that ejected vast quantities of nickel and zinc. Another suggested the comet had passed through the debris field of an exploded alien artifact billions of years ago, collecting metallic shrapnel, Mainstream science pushed back, urging caution. We have a sample size of 1 for this kind of object. To leap to extraordinary conclusions is premature, but the data was undeniably profoundly strange. In December, as the expanding cloud of 3I Atlas crossed Earth's orbital path, at a safe distance of 167 million miles, the James Webb Space Telescope had its second look. The near-infrared spectrograph was now pointed at a diffuse and faint ghost of a comet. The spectrum was a complex tapestry of molecules. The water and carbon dioxide were there, as expected, but Webb detected more: ethane, methanol, and, in trace amounts, complex organic molecules, glycol on a trial, a potential precursor to adenine, one of the 4 nucleobases of DNA. This wasn't entirely unexpected. Solar system comets like Hale-Bopp carried a rich inventory of organics, but finding them in a relic from a star system billions of years older than our own was a profound discovery. The building blocks of life are not unique to our corner of the galaxy. They are ancient, and they are interstellar. The chemistry for life has been available for a very, very long time. The Atacama Large Millimeter, Submillimeter Array, ALMA in Chile, provided the final, crucial piece of the puzzle in early 2026. By studying the microwave emissions from the cyanide molecules in the dissipating cloud, the ALMA team was able to measure the ratio of carbon-13 to carbon-12, and nitrogen-15 to nitrogen-14. Isotopic ratios are like fingerprints for cosmic objects, telling us about their birthplace. Our solar system has a very specific set of isotopic fingerprints. The ratios measured in the remnants of 3I Atlas did not match. They were consistent with the chemical evolution models of the Milky Way's thick disk, from a time 7 to 9 billion years ago. The comet was definitively a product of the old galaxy, an ancient mariner carrying the chemical memory of a long-dead star. By March of 2026, the story of 3I Atlas was functionally over. The cloud of its remains had grown so diffuse it was undetectable by all but the most powerful telescopes. It was outbound, coasting back into the interstellar void at 58 kilometers per second, not as a single object, but as a trillion tiny ghosts. A diffuse stream of dust, ice, and gas that will slowly spread out over millions of kilometers as it continues its journey through the Milky Way. So what have we learned? We learned that interstellar objects can be deceptive, wearing processed crusts that hide their true nature. We learned that the building blocks of life are widespread and ancient, present in star systems that formed when the universe was young. We learned that the chemistry of the old galaxy, the thick disk, is subtly different from our own neighborhood. And we were confronted with a mystery, the nickel, that we still cannot explain. It stands as a stark reminder of our own ignorance. There are processes in this universe, either natural or otherwise, that we do not yet comprehend. David Jewett summarized it best in a lecture in April 2026. He said, "We thought we were observing a bullet. It turned out to be a clay pigeon, shattering at the moment of peak illumination. But in shattering, it scattered its secrets across our sky." We will be analyzing the fragments of 3I Atlas for decades. It was a messenger that consumed itself to deliver its message. The comet is gone, but its data remains, a torrent of numbers sitting on servers around the world. In those numbers are the clues to the formation of other solar systems, to the chemistry of the early galaxy, and perhaps to questions we haven't even thought to ask yet. The Vera Rubin Observatory will come online soon, promising to find dozens of these interstellar travelers every year. We will have more bullets, more clay pigeons. We will build a catalog of these visitors, and the strangeness of 3I Atlas will either become a new normal, or it will stand out as an even greater anomaly. For now, it remains our most detailed, most explosive, and most enigmatic glimpse into the galaxy that lies beyond our own shores. A reminder that the universe is not only stranger than we imagine, it is stranger than we can imagine, and it's coming to visit